potentially have to operate the equipment outside of its design regime, right? But only for a short while. So that's what FFS is for. It is to enable you to do that. So FFS has 14 chapters, 14 chapters, but chapter 1 and 2 is just intro. Okay, so chapters 3 to 14 are your assessment methodologies. So not all FFSs are used commonly, right? The most common FFS use actually is the one that I am presenting here, to be honest, 4 and 5, because this deals with how to deal with when we have a lot of corrosion or erosion, basically wall thickness loss, right? Which can be quite common. Okay. So there are other chapters in FFS like dealing with brittle fracture. So when, for example, you want to run your equipment colder than what it is designed for, or creep. Creep is if you run hotter than what it's designed for. There's FFS for crack, right? If you have a crack, can you continue operation? Some of it is more advanced than others, right? But in my opinion, parts 4 and 5, which is regarding corrosion, erosion, wall loss, is very applicable across upstream, downstream. I will even say outside oil and gas also, I'm pretty sure this is also quite applicable. So yeah. Okay, next, what is part 4 and part 5? So the part 4, the title of that part 4 assessment is called General Metal Loss Assessment. Okay, so general metal loss basically means that if you have corrosion that is quite widespread, right? Then you the preferred method is to use that part 4 calculation method. Okay, the other one is localized metal loss, right? Part 5. Part 5 is usually used when your corrosion or your wall loss area is quite small but deep. Okay, but even though that is the definition, there is no strict rule to basically, there is no strict rule in applying one or the other, right? To be honest, one common practice is that we use both together. For example, we use part 4 first, and then if it doesn't pass the part 4 calculation, we do part 5, okay? Because part 4 is more conservative than part 5 in terms of giving us the answer. Okay? So I would say treat part 4 and part 5 as like partners, right? And they complement each other. Some companies jump straight to part 5 without doing part 4. That's also fine, to be honest. But as I will explain later, kan, there will be some pantang larang lah. There will be some things you need to follow in terms of the rules of applying part 4 or part 5. Okay. All right. So that's it for introduction. I'll pause dulu if there are any questions.
Yeah, one question from Imran. He's asking if there is any slide to be presented, or because currently we are seeing 579 example problem. So we are going to go ahead with the. Okay,
Betul.
all right.
So
okay.
Yes, correct. You are meant to see this problem dulu. So what we are going to do is the main focus of this presentation is to go over the problem example. Okay, that would be the bulk of the presentation. Tapi as needed, kan, we will jump into a few other pictures, images, files that I want to share as well on my phone here. Okay. Tapi for now, yes, I am intentionally nak cover this example problem dulu lah. Okay. So don't worry, you're not missing anything. Okay. All right. So okay, if there are no further questions, okay, so let us jump straight into an example problem lah, and then I will do the explanation and the macam introduction as we walk through the example. Okay. So if you have if you have paper or pen or notes, kan, I would highly suggest that you would take some notes or follow through the exercises, kan. So for the exercise, we are going to do some of the calculation, but for time's sake, there will be some parts where I will just show you and walk through with you the calculation, but no need to write it yourself. You get what I mean? Because you know, these calculations can be quite long and I don't want to waste time. It's more important that everyone understand the basic concept lah. Okay, so let us jump into an example problem here. Okay, so in this particular example, all right, So we have a pressure vessel, okay, which is an equipment. If anyone is not familiar with what a pressure vessel is, wait a minute. Later I will show something. But yeah, this is an example of a pressure vessel. And the area that you see here is basically an area where quite severe corrosion has happened. Okay. And basically, we have some data on regarding the equipment here. So we have the material that the vessel is made for, design condition, ID, nominal thickness, all of this. Okay. So let us walk through this one by one. Okay. So let us start with material. So pressure vessels or piping, they are built with steel material, right? Most commonly, and each steel has its own grade, right? It is a grade that is usually specified by the SME code. But if your vessel is not designed per SME code, it's some other code lah, right? But it will always have a code of numbers and letters that is easily traceable. Okay, so so SA516 grade 70 is a pretty common material type for pressure vessel. Nothing special there actually. Okay, design conditions. Okay, so this is where I want to highlight a bit, right? And I hope people take notes here. Okay, so when I shared about the definition of FFS just now, right? FFS is about um, running the equipment beyond its design condition. So by definition, we have to find out what the design condition is, right? Betul tak? So that I would say is the most important thing, because if let's say we are not clear about what is the actual design condition, aka what is the minimum required thickness for that equipment to run at say 300 psi, then we do not know how bad is bad. So let's say that for this vessel, like just an example, the minimum thickness is, we go at site and we measure, and let's say we measure it and then we see a thickness of 0.5 inch, for example, again, 0.5 inch. How do we know exactly that 0.5 inch is okay, good or bad, right? We need to have a benchmark lah. So that benchmark is related to that design condition. So, okay. When we talk about pressure vessel, I'll start with pressure vessel dulu. The most common design condition that people would know is internal pressure. Okay, so pressure vessel needs to contain pressure internally. And when it contains pressure internally, it contains a certain value lah, like in this example, 300 psi of internal pressure. And it contains that by having a certain amount of thickness at a certain temperature. Okay, a higher temperature would mean that the vessel material becomes weaker. So 300 psi at 100 F versus 300 psi at 350 F, a vessel at 100 F can be thinner than 350 F, even though they contain the same pressure, because you need more thickness to compensate for higher temperature because material become weaker at higher temperature. Okay, it's the basics lah. Alright, so how do we know exactly what is the minimum thickness that we need for internal pressure? So let me just scroll up sikit. Okay, alright. So
Jason?
Yeah.
Okay, so sorry, one question from Nurihan. Nurihan, tadi ada angkat tangan. Nurihan, you want to ask tanya?
Okay, Cik Dizon nak tanya. Normally kita akan buat FFS ni when the thickness reaching T minimum. Betul ke?
Betul.
Okay, so dia tak perlu tunggu, macam adakah T min tu is too late? Sebab dekat dalam API 574, kalau untuk piping kan dia ada T alert kan. So FFS ni kita tunggu thickness tu dekat T alert ataupun dekat T min then we do FFS.
Good question. Actually, tak apa. I will answer that very soon once I cover piping kan. Can you hold that question dulu?
Okay,
tapi
boleh.
just as a very quick punya answer, generally kita nak tunggu until the T-min tu sampai. It doesn't have to sampai right now. So let's say that you measure something and it's pretty low sekarang, and you know that based on the corrosion rate yang dah bertahun-tahun you have measured, it will reach that in 2 years. then that is okay dah. Yeah, that is an okay trigger to do it. If let's say you know that in the 2 years tu, you don't have an opportunity to repair it, right? Like you know it's going to come, even though it hasn't come now. Itu pun boleh do the FFS lah. But you need to wait until the actual teaming. On API 574 tu, I have something to share lah. Tapi can you hold back a bit on that? Well, we'll get to piping. Okay, let me quickly finish the vessel punya point dulu. Thank you for that question.
Boleh.
Okay. Alright.
One more question boleh?
Boleh. Sila.
Okay, from Kushairi, a general question. In API 510, there is a section to evaluate metal loss and pitting. Is that considered as level 1 FFS or not even yet considered as level 1?
So basically from what I hear, the most latest update of API nanti is of API 510 will say that is not FF. I can't remember lah. Okay, I'll be honest. I have to go back on that one. So macam what I know is that API 579, API 510 have this overlap, right, regarding this procedure of evaluating pitted condition, kan? What I know is that in the latest update, they're going to make it a bit separate. So 510 has its methodology and 579 would have its own more advanced methodology. So the intent is buat API 510 dulu, then baru go to 579. Yeah, but to be exact, whether that particular pitting calculation in API 510 will be considered level 1 ke tak tu, I'm not sure. Macam it could be that thing still remains in API 510 while API 579 use something more advanced, ataupun the whole pitting thing masuk API 579 dan API 510 just kata no need to assess ke apa ke. I'm not sure between those two scenarios which one is the correct one. Yang tu tak apalah, I will take it back as a follow up nanti. Okay. If you don't mind, I will proceed dulu, boleh? Okay, so alright. So ada question lagi ke? Hello? Sorry.
That's the two question. Thank you.
Silakan if there are any more questions.
No more question. No, no more question, Lisa.
Tak ada? Okay, alright.
Tak ada.
Okay, just let me know bila I can resume.
Please resume. No more question.
Okay, sorry. Tak apa siap pendengaran, not so good. Anyway, okay. Alright. So, like I said just now, our someone mentioned teaming, kan? So teaming is tied to the design condition lah. So example just now, vessel 300 psi. I hope people can see my screen. I'm just showing some general formulas and notes lah. So for internal pressure, tak boleh zoom dah. So at the top left corner, you can see the internal pressure. Basically, you have a formula tied to it. For example, for shell, it's PR divided by SE minus 0.6P. Okay, so you will be using this formula nanti lah in your exercise for internal pressure. Okay, internal pressure is the most common thing you calculate for pressure vessel, but there are some other key design conditions that you should pay attention juga. One is called external pressure. So external pressure does not affect many vessels, but it can affect vessels where macam if I take an example, if let's say there's a vessel and then just downstream or upstream of that vessel there is a pump or a compressor that is continuously sucking the content of that said vessel. Okay, so what happens kan is that the vessel will have a vacuum inside of it, right, such that di luar outside vessel tu dia ada atmospheric pressure biasa je, tapi sebab dalam tu ada vacuum, the vessel kena ada sufficient thickness supaya it doesn't crush like a tin can. Okay, if you can imagine it, right? So when we talk about external pressure, it doesn't mean that there is some very super strong pressure or gravity or anything outside, but rather there's a vacuum condition inside the vessel and you need to have sufficient thickness. So external pressure ni can be easily found in a drawing. For example, it will indicate that the vessel is designed for vacuum, for example. So, and to do that calculation, it's a bit more advanced than the formula T equal to PR SE ni. Basically, the important factor you need to know is the length of the component. So, without going into too much detail, basically, if you have a longer shell, you are more susceptible to external pressure. Okay, so if you have a longer shell, you need a thicker shell to withstand external pressure. Okay, and you have to compare internal versus external pressure. The higher Tmin is the one that you will need to use. So for example, we have a vessel yang maybe as for PR over SE dia maybe 3 mm. Based on external pressure, calculate length dia, length over diameter ratio, blah blah blah, apa semua. You need 5 mm. Your vessel Tmin has to be 5 mm. You need to do FFS if it goes below 5 mm. Okay. When you have nozzle, so on the right here, I'm showing, this is an example of a nozzle. This is like a macam cutaway section of a nozzle. Basically, there's horizontal portion there is the shell, and then there's the nozzle protruding. Nozzle also has internal and external pressure concern, like normal shell, but there's also this thing called reinforcement. To put it very simply, when you have a nozzle, you are cutting a hole in the shell. When you cut a hole in the shell, you have to make sure the metal that used to sit in that hole is compensated with neighboring material. Sebab tu, many nozzles have this thing called a reinforcement pad dekat tepi the nozzle. So the edge of the nozzle is thicker so that it can have that compensation so that it becomes reinforced, right? If you have a hole in the middle of the shell, that hole becomes a weak point, a stress concentration, and you need more reinforcement on it. Ada certain formula to find out that reinforcement. Okay. Almost done on vessel design basics. Internal pressure, external pressure, nozzle reinforcement. Another thing is, drawing ni tak cukup besar. Okay, so drawing ni besar sangat. When you have tall vessels, you are also subjected to wind. So when you have wind, Winnie, to put it very simply, Winnie is very difficult to assess using hand calculation. You probably need some software like PV Elite or something to assess it, right? And it doesn't affect all vessels. Typically, the tallest vessels they get affected by it. To put it very simply, the software will calculate what is the wind velocity. Wind velocity based on region lah, Malaysia versus Singapore versus Rotterdam ke apa kan. So different wind velocity. Based on the wind velocity and the area of the shell exposed to the wind, you will get a force, kan? And then from the force, you factor in the thickness of the shell. You would basically find out what is the stress that is caused by the wind on the shell, okay? And this stress from the wind, it can actually be higher than internal, external pressure. If it is higher, then you may need to consider this and do FFS if it doesn't lepas this thing. So I'll give you an example lah. So for example, a tall tower, kan? The internal pressure is low, so maybe 3 mm is the required thickness after buat P equal to PR over SE formula. Do the external pressure pun not so high, right? So maybe around 5 mm for example. But because the location is high wind area and the shell is located slightly at the bottom area, then the stress becomes very high. It could be 7 mm needed due to wind. Then 7 mm should be your benchmark for ni lah, for apa? Tmin. And if you reach 7 mm, you need to do FFS. Okay. I'll pause first on vessel. Any question?
Yeah, question for Muhammad Azhanuddin. Dia tanya, does FFS cover jacket or stiffener support assessment for FFS 4 and 5?
So stiffener is covered in the sense that it will be, so let me think. Stiffener, okay, so a stiffener, whether you need a stiffener or not, right, is covered by normal SME calculations. Okay, so normal SME external pressure calculation will tell you whether you need a stiffener or not and where you need to put that stiffener. As to how big the stiffener ring has to be, that is covered by also by SME code, I think. What FFS does about stiffener ring is that FFS will calculate whether stiffener ring that you have, is it going to be limitation for FFS or not? To put it very simply, if you have stiffener ring that's too big, then you cannot do part 4 and part 5. You have to go all the way to like finite element essentially, because it's like a area of high stress concentration and called discontinuity lah. So to put it short, for stiffener ring, it is something important to consider in FFS, but it doesn't tell you how big it needs to be lah. It's more of kind of like you just want to do a check whether you can do FFS or not, if there is a stiffener ring or not. As for jacket, basically you would treat jacket as ni lah apa? I mean, assuming if you're talking something like a double jacketed thing where there is another pressure acting on that jacket, then it will be that pressure that's acting on that jacket lah. And yeah, it could be applicable as well. Yeah, for FFS. Okay. Any more questions on vessel? Yeah.
Sorry, my question is actually, like if you have a vessel with stiffener, then all the other shell part is okay. Then only the stiffener have corroded attached to the vessel lah. Then can we do the FFS assessment on that lah, and on that particular region which corroded, localized?
So basically you're saying that the area that is close to the stiffener is the one that is localized corrosion. I think this is pretty common, right? I mean, I assume like CUI or something like that, right? Yeah, then you have that. Yeah.
Yes, yeah.
Yeah, that's the tricky part. It depends on the size of the stiffener ring. Okay, so part 4 has a guidance on what is the size of the stiffener ring that is allowed to basically not considered as a discontinuity lah, they call it. Okay, so macam to be honest, in my experience, the ring has to be very big for it to not be able to do FFS. Most of the time, it should still be okay. Tapi if the ring is really big, then it is an obstacle because when the ring is too big, essentially a big component usually has, you know, a big well attached to it juga kan, if it's thick and all kan. So that causes a area where basically you can have stress yang that is higher, right? Number one, residual stress from the well. Number two is when you have two thick big components adjacent to each other welded, there is a lot of stress when they are trying to move even in a small displacement. So that is like that is the reason why typically if you have a very big stiffener ring or you have a very big macam weldment that is weld to a different shape, contoh cone to shell or something like that kan, FFS cannot be done. So sorry for the long answer. Short answer is boleh, typically boleh, but you need to evaluate the size of the stiffener ring, which usually should be okay lah. Sebab stiffener ring pun corroded kan selalunya. Usually stiffener ring is also corroded, so usually the size is okay.
Okay. Thank you, sir.
Welcome. Okay. Alright. Any other question tak before I move to piping? Because I want to answer apa? Cik Nurihan, Puan Nurihan punya answer question on piping. If not, I proceed dulu to piping. Okay. Yes. So for piping, we have internal pressure similar to apa? Vessel also has its own PD over S formula tinggi kan? Okay, has that. This is the value from the API 574 table that Cik Nurihan was sharing with us just now. So in API 574, basically, before I go there kan, I think if you don't mind, I will quickly go back to our example problem tadi to give a bit more recap back to FFS. Sorry. Okay, sebab tadi I talk a lot about pressure as design condition. Okay, forgive me Dan just nak check something. Mana dia tu? Supplemental loads. There should be a note on supplemental loads. Sekejap okay, there is no note. Okay, maybe it was in the other problem code. I'm sorry. Okay, so there is this phrase called supplemental load. So what does supplemental load mean? Supplemental load means basically wind and weight. Okay, for vessels it's typically wind. For piping it's basically weight. Okay, so pressure, external or internal pressure is what we call a common load lah, right? For this equipment. But wind and weight are also loads that we need to consider lah in the design. So when we talk about supplemental load on piping, which is weight kan? Okay, actually there are two ways of evaluating whether piping needs, whether piping is thick enough to support the weight of its, valve or flange or some other thing on it, okay? The simpler way is like what Cik Nurihan was saying just now, is to use the API 574 table, okay? The 574 table is a easy rule of thumb where depending on what size your piping is, you can see what thickness is required to support the weight. Okay, so and then this table has a alert thickness and a minimum thickness. So in my sharing here ni, I'm just showing minimum thickness je. Tapi there's also an alert thickness such that if let's say some site or company doesn't want to wait until the absolute minimum, they want to be more proactive, they can use the alert punya value. Okay, so maybe for example here, you can see 3 inch is 2 mm. Tapi that is the absolute minimum. The alert I think was 2.3 ke 2.4, tak ingat lah. Tapi yeah, it's thicker than that lah. Okay. Alright, so that's the simple way. There is a more bukanlah advanced I would say, but a more engineering way lah to calculate the actual thickness you need to sustain those weight. Okay, so benda ni it takes us back to university days lah. Sekejap this is an example. Ni actually screenshot from Google je lah, but this is an example where if let's say your piping is lower, your piping cannot meet that API 574 minimum thickness, right? What you can do instead of FFS is to actually apply some engineering calculation to basically determine what is the thickness that you need. So in this example problem here, you can see that there's a uniform weight kan, 12 pound per inch, and then the piping, there's a span between the support and the piping is circle shape lah kan. So you can do some engineering calculation, right? Macam apa, mechanic of material, solid mechanic, all that, right? You can use Excel usually to do this, and you can determine what thickness is actually needed to support this weight, and it typically is lower than the number that you need in API 574. So this is a not very common assessment, okay? Understandably so lah, because it obviously takes time and a bit of skill. Tapi the what I want to share mainly here is API 574 is not necessarily the end of the road, but API 574 thickness is quite low already, such that if you want to be careful, you should, if kalau boleh repair, you repair it lah, right? Not even think about FFS actually. If you can repair, just repair it. But if you really cannot repair it, then you can do detailed engineering calculation first. If the detailed calculation shows a value that even you cannot meet, then only you do FFS. Okay? So I will pause there. So that is my take on piping. Okay? And this is focusing more on weight lah. So maksudnya the weight of the piping, the weight of the valve or anything, right? It's going to add to the example that I showed just now, yang the weight on that piping section. So, Cik Noreha, I'm sorry if that is a long answer to your question, tapi that is the complete answer lah. I'll pause here dulu if there are any questions.
No question on the chat, but if there is, if anybody would like to ask any question before we proceed, please.
So, okay, so I think I enough dah cakap about the design part of it lah. I'm sorry if I went a bit too deep or too detailed on this part. Tapi I think that it is important to really know what your equipment is designed for, baru buat FFS, because see, FFS needs data, right? So you're basically sending people to get inspection data, and if you actually don't really need it, you actually can use engineering calculation pre-FFS to settle it kan. Then it is much better for everyone lah, right? Okay, alright. So I'm just going to do a very quick recap on the design part. Okay, if you don't get anything else from all the detail that I cakap tadi, to be very simple macam ni. For vessel, you should know that there is internal pressure, external pressure, wind, and nozzle. Okay. For piping, there is internal pressure and weight. This is not all of it lah, tapi this is the most common one, 95% lah. It covers the case. Okay? Alright, so once you factor all of those things in, and you confirm that, okay, I know what is my minimum required thickness for my component, memang you have to do FFS lah kan? Okay, then you do FFS lah. Okay, so we go back to the problem. Okay, thickness, all of this nothing special. It's just regular dimensions. Sekejap, let me do a check on time. Yeah, I'm doing 9:06. Okay, boleh sempat. Okay, so future corrosion allowance. Okay, so when you do FFS, like I said just now, you can do it when you actually find a corroded area right now. Like memang ada problem right now. Tapi if let's say you have a problem that you know is going to happen next year, because let's say the fluid is very corrosive, and you don't have time to repair it, then you can also do FFS. And typically, this is where the future corrosion allowance comes in. Basically, this is a value that you can specify in your calculation to determine how much you need lah. So, if I give an example here, sini example dia 0.1 inch kan. So, maybe what's happening here is, let's say, the corrosion rate is 0.2 inch per year. And 0.02 inch per year. And katakan dia tak boleh repair in 5 years. So 0.02 times 5 years is 0.1 inch. They need 0.1 inch to safely operate. Right? You can put your own future corrosion allowance based on what you need lah for your business. Okay? And then weld joint efficiency. Weld joint efficiency is just a number that will be used in your PR over SE calculation later, okay, for design. Okay. FFS, like I said, requires inspection data and very detailed one. You need a grid, right, with proper thickness taken. All the engineering calculation and design I mentioned earlier does not need proper thickness like this. So this is pretty intensive lah. So make sure you really know, if you want to do FFS, you really need FFS. Okay. Okay, so we have here an example of the data lah, okay, and this is very beautifully plotted, okay. So you have apa plane kan, they call it the C plane and the M plane, and for each of the plane you have the thickness, okay. So this is nothing, I would say nothing too, I would say out of the box lah, so to speak. You can see in the middle, intersection of M4 and C5 is your lowest point lah, 0.36 inch measured, okay. And then as you can see here, the perimeter, maksudnya the outer edges of this grid kan, is all 0.75 kan. So what this means is that when we do thickness measurement for FFS, we want to take the thickness such that we cover up until where the thickness is acceptable. Okay. And the definition of acceptable is that it is close to nominal thickness. Okay. Basically, we want to scope out the thickness measurement sampai the areas where they okay lah, okay, where they okay, where macam the thickness is lebih kurang sama macam original, there is no damage, so that you can completely capture the scope of the damage lah. The basic concept of FFS, whether 4 of part 4 or part 5, is basically the concept of borrowing from neighbor lah, senang cakap. So 0.36 ni very nipis kan, but you can see that it is neighbored by 0.58, 0.58, 0.59, 57 kan. Can the neighbors pinjamkan the strength of that particular weak point? That is the basic concept of FFS lah. Okay. And all this fancy math is just, it boils down to that. It boils down to whether the neighboring area can supplement the strength of a very corroded area. Okay. Okay, I'll pause dulu. Then we can jump into our exercise lah.
Question from the question. Okay, Muhammad Zanuddin asked any specific grid size spacing required
good
by
question.
FFS
Thank you for asking that. Betul. Thank you for asking that. So, general rule of thumb. Okay. Finer grid is better, kan? Smaller grid is better. Tapi, I would say that 2 times nominal is the max that you can go lah. That's the biggest grid that you can go. Okay. 2 times nominal thickness. 2 times nominal thickness or smaller. Okay. There is a proper formula in API 579 that will give you the grid size based on the measurement that you have. Tapi dia macam chicken and egg sikit. It's like, how can you measure if you don't know the grid size? But the formula calculate grid size, I mean, before you can measure kan. So it's like, which one comes first? So typically people would do nominal thickness or half of nominal thickness or something like that lah kan. Macam, but the finer you can take, the better. Okay. Alright, let us jump straight into the exercise lah. So like I said just now, we are going to do the exercise on some of the initial calculation, tapi maybe for some points where the calculation dah jadi too leceh lah, I guess, terlalu leceh. I am just going to walk through the calculation, okay? Because yang paling penting, we want to share basic concept. Let me take a sip. Minum. Okay. So first thing is that let us calculate the minimum required thickness. So I hope you are familiar now with the formula I mentioned just now, PR over SE minus 0.6P, kan? Okay. So, alright. Basically, for this one, I think it's okay. I give a bonus lah for this. You don't have to calculate this first. Okay. So, you can just copy or just take note what is the thickness that is recorded here. So, you can see that there's a TC and TL value here, kan? So, TC value is internal pressure. TL pun is also internal pressure. But basically, internal pressure in a pressure vessel, it works in two directions lah, senang cakap. Basically, there is the longitudinal, which is TL, longitudinal kan, and circumferential. Okay. More often than not, circumferential governs lah. Okay. Usually kan, longitudinal ni akan govern bila dia ada wind yang membantu dia juga. So typically, is longitudinal plus wind boleh overrule TC. Tapi if tak ada wind, in this example, wind effect is probably negligible. TC dominates lah. And you can see your Tmin is the max of the both and 0.43 inch. So for time benefit, let's copy 0.43 inch dulu lah. Okay. Any questions tak regarding this particular calculation? The factors, I think many people here are quite experienced. So you may know already, P is pressure, R is the radius of the shell, S is the allowable stress of the material. Tadi kan SA 51670 kan daripada atas. You can look into your SME code table to find out grade 70 ni berapa dia punya allowable stress. Allowable stress is different from yield stress or ultimate tensile stress. Allowable stress is much lower than that lah because nak jadi konservatif kan, ada safety factor. E is called joint efficiency. Basically, this is a function of how much inspection do you do on the well. In a vessel, well is a weak part. I mean, even piping, so well is a weak part. And you need to make sure that if you do full inspection, rajinnya, you do all inspection of the well, everything okay, then you can take E equal to 1. Tapi if you do a spot check je, maybe E equal to 0.85. If the well is instead of double butt well, it's a single butt well, jadi 0.8. So it kind of depends on the quality of your well and also the amount of inspection that you do on the well in the design stage of the vessel. Benda ni is very clearly indicated in vessel drawings, so it's not something difficult to find. So you do PR SE minus 0.6P, dapatlah the value. Okay, I'll pause here for this basic Tmin calculation for internal pressure. Any question? Okay. Okay, so far everyone okay. Yes. Tuan Syed, I think I susah sikit nak buka from chat. Nanti kalau ada any question from chat, just Roger to me. I will help answer terus.
No problem. No problem.
Tak ada question Okay,
So
saya sambung.
None from chat.
Okay, boleh. Alright, so next is that, okay. Alright, saya akan tunjuk sampai step 4 sahaja, okay? Step 4 sahaja bonus So, step 2 is basically kita kena find out what is our lowest thickness. Tadi kan I show you that 0.36 is the lowest thickness kan? As you can see, 0.36 dah below 0.43. Ni trigger lah for FFS kan? Kalau thickness tu 0.5 ke, that means above 0.43, buat apa nak buat FFS? Unless you can repair it in the next 3 years ke apa-apa ke. Okay? Alright, step 3 is determine the wall thickness to be used in this assessment. So what this means is that, okay, tadi kan when I mentioned to you that the measurement is done up until the area where the thickness is okay. Let's go back to the grid again. 0.75 is the perimeter lah where everything is okay. And then 0.1 is our future corrosion allowance just now. So like I said, in this example problem, 0.75 is the okay thickness. Tapi we need 0.1 atas balik 0.1 future corrosion allowance to basically protect us for the next few years yang kita tak boleh repair. In this example lah. Okay. It could be any other number lah, this future corrosion allowance. It's basically set by the owner of the equipment. So we basically, as a benchmark for our calculation, we take the original undamaged thickness minus how many FCA kita ada, so 0.65. And then what we do is we basically do a thickness ratio. Okay, thickness ratio is an important factor. So thickness ratio is, to put it very simple, the ratio of area paling teruk to the area yang okay. Alright, that's the simplest definition lah. So 0.36 is yang paling nipis, minus lagi 0.1 FCA tu, divide by 0.65 yang kita dapat dekat atas. So essentially it's like area paling teruk divide by area paling okay, tapi dua-dua tolak FCA. Okay, so this ratio will play a big role. Okay, so keep that in mind. Okay, so next would be, okay, this is nice. Okay, step 5, compute the length for thickness averaging. Okay, so I want you all to basically, now kena ada latihan sikit lah. Ada exercise sikit, the calculation part. Let me find the file for the RSF calculation. Sekejap RSF formula tadi is in this one. Should be this one. Okay, sekejap The screen cannot turn I hope people are not seeing it macam upside down ke? People are seeing it upside down ke? I hope not. Ke it's just me? Is it macam upside down ke tak? Can anyone help update me? Hello?
Okay, dia okay.
Okay, okay. Sorry. Yeah. Just want to make sure. Sorry, sebab in my maybe my view kot dia upside down. Okay, so okay, the exercise here that I want people to do is to do this calculation, the equation for Q ni. So jangan guna 50, guna yang atas tu. 1.123 in bracket 1 minus RT. RT tu thickness ratio kita, which is 0.4 kan. Tadi kita dah calculate the ratio of paling teruk tu paling okay. Divide by 1 minus RT divide by RSFA tu. RSFA tu ambil 0.9 0.9 is a default value lah in FFS. It is a most typical macam constant lah kita kata. Okay. RSF, remaining strength factor. Letak 0.9 for that. And then square kan tu ada minus 1, lepas tu square root kan balik. Okay, so this is the math part that I expect people to do lah. And I'll give a few minutes for people yang want to do this calculation. So, in the meantime, while people are doing it, I'll just quickly explain. Okay, apakah signifikannya Q ni? Q ni signifikan dia adalah, from this Q constant, we will get what is the length yang kita boleh do the averaging. Okay, kan dah I say example just now, tempat paling nipis tadi 0.36 inch. Neighbor dia 0.58 kan? 58 is above than 0.43. So neighbor dia kuat lah. Okay, neighbor dia is good. How much of dia punya neighbor yang dia boleh borrow? So kita calculate Q ni to get to that. How much of that kita boleh borrow? Boleh borrow fully ke? Boleh borrow separa ke? Okay. But it'll start by calculating this Q part lah. If you use software will calculate automatically for you lah. I will wait for a few minutes until someone boleh give me an answer. RSFA tu 0.9 and RT tu is 0.4. I will reveal the answer bila someone give me the first answer attempt. Berapa the value is. By the way, just to be clear, kita tengah buat part 4 assessment. We are in part 4. And like I said just now, if part 4 tak lepas, we can do part 5. Anyone yang dah dapat answer nanti, just shout it out.
0.46 from Nurihan.
Nice. I think that is the correct answer. Let me double check. Okay. 0.46. Nice. Okay, good job. Congratulations, Nurihan. Thank you so much for paying attention. Yes, the answer is 0.46. there is also a table lah where you can read 0.46. So if you saw tadi the table, I'm not sure tadi ada kat atas tu ada screenshot of the table kak. Maybe that is the answer kak. But either way, yeah, you can find it through a table and by the equation. Okay lah. So for the interest of time, I'm just going to walk through the rest of the calculation. Yang penting konsep kan. So okay. So the final number that is important tu is the L value kat bawah ni, which is equal to Q darab square root D dengan TC. Okay. TC adalah yang tadi, which is thickness yang okay minus future corrosion allowance. D is just diameter. Cuma diameter asal vessel kita 48 inch kan. 48 inch kalau tak silap. Cuma kita kena tambah FCA tu jugalah. Again, semua benda kena tambah FCA sebab kita kena forward looking. Okay. So 0.1 sebab dia adalah diameter. So dia macam akan makan on both sides. If you imagine, corrode will happen on both sides. If you're talking diameter, 48.2. Overall, what we want is in the end from step 5 ni is L. L value is 2.564 inches. Okay. Apa significant 2.564 inches ni? Alright. So from our grid tadi, we pick the lowest area, and then as you can see there, we pick that lowest area as a midpoint, and then kita stretch 2.564 inches to the left and to the right of that area. Lepas tu, neighbor dia tebal kan? Ketebalan area kawasan tu, which is bounded by the 2.564 tu, that area tu, kita boleh calculate the area and kita dapatkan the average of the area. Benda ni just geometry lah. So basically calculate area trapezium 2 ni kan. And the calculation ditunjukkan di bawah lah. Okay. I don't want people to go through this lah. Just faham the concept. Cukup So I think this is the key part of the calculation lah, where basically we determine what's the length yang dibenarkan untuk scope the area neighbor untuk nak kuatkan area yang lemah. Okay. And when we talk about FFS, we have grid in both direction. Ini is the horizontal direction. Yang ni is the vertical direction. Tapi the process is still the same. Same L value. Cuma neighbor dia lain sikit sebab kita tengok from vertical point of view pula. And overall, kita akan dapat average of the area. Daripada area, kita akan dapat average thickness lah. Daripada area tu, kita dapat average thickness. So, apakah konklusi from ini? Semua adalah 0.36 was our lowest thickness. But because the neighbours are thicker, we can consider 0.426 as the, I would say, reinforce. I don't know, it's like the FFS thickness lah kita kata. The FFS thickness is bump up to 0.426 daripada 0.36. Okay? Because of borrowing from the neighbor. I'm going to pause here. We are almost at the end of part 4 already. Okay tak? Any questions? Software will do all this for you lah. This is basic concept. Just to for understanding is okay. Okay, we're good Then after that,
anybody who wants to ask? Ada ke siapa
Apa dia?
nak tanya?
Yeah.
From the group ada siapa nak ask question ke? Okay, tak ada. Thank you.
Okay, nice. Okay, I hope the content is okay lah Okay. So step 7 is basically just a direct comparison lah. Remember kan our minimum thickness just now was 0.43 kan from step 1. Tapi kita punya lowest thickness yang kita dapat tadi adalah 0.426. 0.426 masih lebih rendah daripada 0.43. So dia masih tak satisfied lah. So basically itulah. And essentially it is not satisfied in level 1, and level 2 pula is still part 4. Basically it's just 0.43 thickness yang diperlukan tu darab 0.9 tu saja. And ini pun tak lepas juga because our lowest thickness is 0.326 inch tadi on the other direction. Okay. So let us recap lah part 4. Part 4 recap is, let me go back to this graph. Okay. Part 4 recap. Basically measure thickness in grid. calculate the ratio. Ratio adalah tempat paling teruk versus tempat yang okay. And then calculate the length that is okay for us to do this averaging. Sum up the area, average kan, jadi an average thickness. And then compare balik average thickness against the original T-min. If tak lepas, tak lepas lah. Okay. So that is it for part 4. Part 4 is quite graspable lah. It is something that is quite okay to grasp, I would say. For the interest of time, if you don't mind, I will quickly go over part 5 juga So
the screen nampak macam kecil lah.
Sorry. Sekarang better tak?
The screen. Dia nampak kecil. Mungkin dia horizontal or vertical punya screen.
Sekejap I don't know if I try to share balik, lepas tu unshare will work or not. Sekejap Let me stop share. Share balik. Sekejap Is it still okay tak? Ke besar lagi? I'm trying to zoom. Is it better now? Ke kecil lagi? Tuan Syed, hello? 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 Hello?
Cikgu, kita orang tak nampak screen.
Oh, okay. Maybe tadi sharing tak berapa jadi je Rasa saya dah tekan share dah. Audio, share screen. Start now. Lepas tu, jap Please give feedback kalau nampak screen kita. Okay, now nampak tak? I am showing example problem 1, part 5. Nampak tak?
Okay, nampak.
Okay, and I hope the size is okay Alright.
Yes,
Size is okay.
Thank you so much. Okay, let's proceed to part 5. So, part 5 data requirement is the same as part 4. Dekat sini tulis supplemental loads negligible. Sorry, I was trying to find this lah, supplemental load bila cakap pasal wind dengan weight tadi. Sorry Okay. The data requirement is the same. Kita masih ada grid Okay. Sama gak grid. This time different vessel pula kan. Example grid. Okay, mana lowest thickness tu ada 0.47 tu paling nipis. That is very nipis. Paling okay 1.15 tapi 0.47. Nampak tak? Ratio dia 1/3 kot rasanya. Or maybe half lah, half. Half tu dah macam indication that it is okay to do FFS tapi dia tak ada full guarantee whether akan lepas ke tak lah, so to speak. Right? With experience, you'll be able to tell jugalah. Kalau katakan ni 0.1 dah tinggal kan, tak payahlah nak FFS, just repair je. Give up. Okay? Alright, so okay, let us walk through the calculation. As usual, I akan tadi ambil a very one part of the calculation for manual lah, just for exposure kan. Tapi yang penting I want to walk through the basic concept. Okay, I hope they will be better for our timing lah. Okay, so similar concept tadi, kita kena calculate T sub C, which is our okay thickness minus corrosion dan future corrosion allowance. In this case 1.025. Sama macam tadi. Determine the minimum measured thickness. Okay, minimum measured thickness tadi tu 0.47. Tadi kita dah nampak tadi kan. Okay. Now in part 5, apa yang penting adalah the length of the floor. The total length. So S value ni adalah 8 darab 0.5 So 4 inch. Okay. So 8 darab 0.5 tu kita dapat daripada grid tadi. Let me go back to the grid. So if you see the grid tadi, dia ada 1, 2, 3, 4, 5, 6, 7, 8, 9. Dia ada 9 columns kan. So, sekejap 9 columns. Betul ke tak ni? Sekejap The length of the floor is, sekejap nak double confirm. 1, 2, 3, 4, 5, 6. Okay, so basically, okay, the grid tadi tak berapa clear lah. Tapi when you draw it in this shape, you can see that the white area ni dia cover 8 horizontal grid. 8 and satu grid tu 0.5 inch panjangnya. So 8 darab 0.5 is 4 inch. Okay. So the length ni penting in part 5. Kalau part 4 tadi, The length tu kita hanya nak tahu sebab nak average kan. Ni the actual length of the damage is going to play a big role in part 5. Part 5 will help us get more credit daripada part 4. So, we go back to, okay. So S equal to 4 inches. S ni adalah the longitudinal length of the area. Okay. So next is the thickness ratio. Thickness ratio ni sama macam tadi, sama macam part 4. Lowest thickness minus FCA minus thickness yang okay minus FCA. So 0.3366. Okay, so what I want you to calculate next is basically this longitudinal floor length parameter. Yang ni I want you to calculate yourself. So basically calculate lambda, which is yang ni 1.285S darab D square root D over TC. Okay. So I'm not going to share my screen lah. So please capture the formula. The lambda factor is 1.285 darab S. S is 4 inch. Dibahagikan dengan square root diameter dan TC. As you can see on the screen, TC 1.025, D adalah 96.45. Okay, S value adalah 4 inch. Please calculate. I will wait for you for the answer. Okay. Longitudinal floor length parameter penting. Apa dia?
Turun sikit for the formula. Formula tak nampak.
Tak ada. Sorry, yang ni saya tak nak sebab jawapan tu dah ada terus kat bawah. Saya bacakan the formula.
Okay.
Sorry. Okay, saya ulang balik. Okay, sorry. Lambda adalah 1.285, okay, 1.285 darab S, lepas tu bahagi, dekat denominator bahagi tu adalah square root D darab TC. Not a very intense formula, just nak bagi some exercise. Let me know if you get the answer, okay? Longitudinal floor length parameter adalah length parameter yang penting lah, sebagaimana L untuk part 4, lambda adalah penting lah untuk part 5. For folks who are on the line, jangan risau. I think we are almost at the end of my presentation here. I hope you are still bearing with me. Please feel free lah to reach out to me kalau ada apa-apa specific questions ke apa ke. I'm not covering 100% of everything. I mean, part 4 and part 5 here, I mainly covering the basics. Faham the procedure calculation and applicability lah. But, you know, some of the questions tadi I got was a bit more detailed. So, if you want more detailed consultation, tanyalah. It's okay. Tanya PM tepi. Let me know if anyone get the lambda value tadi based on the formula. I'm going to show the answer once anyone shouts out the first answer. Anyone ada the answer? I'll wait for 1 more minute and if tak ada, I will just reveal the answer. Kalau anyone answer in the chat, please let me know. Sorry, I couldn't able to monitor the chat. Hello? Anyone? Okay lah, 1 minute dah up.
0.517 inch.
Berapa?
0.517.
Okay, sekejap saya pause je. Boleh everyone just wait for a while Just give me a minute Sekejap. Take a break sekejap. I have to go somewhere. Sekejap. Okay, sorry about that. Okay, alright, 0 point berapa tadi? Tuan Syed, sorry terlepas tengah tadi.
0.517 inch.
Nice, 0.517. Okay, thank you folks for staying engaged. Malam Ahad. Malam Ahad kena buat matematik pula. Thank you so much. Alright, so from here onwards, kita walk through je lah the calculation. Longitudinal flow length parameter ni is important lah The longer the value, the larger the value, the lower lah the likelihood of kita nak lepas our calculation. Okay. So there are some checks that we need to do more towards macam number one is our ratio tadi, thickness ratio is 0.33 tu, ratio paling teruk kepada yang okay. Dia tak boleh lebih tinggi daripada, dia tak boleh lebih rendah daripada 0.2 So what does that mean is, if I give example, katakan original thickness 1 inch, tapi corrosion is already at 0.1 inch. So that is like 0.1 ratio already. That is just so bad. It's like FFS will just auto say tak lepas. Okay. So there is a minimum cap lah, right? There is a cap where you just, it just cannot be rescued lah. Okay. Then you have to do something that is more, I guess, more, you have to be more proactive lah. You have to force through the repair ke, or terpaksa change design condition ke, maybe lower pressure ke, or something like that. Okay. And then there are some other checks here. TMM minus FCA ni, that means our lowest thickness tolak the future corrosion allowance tak boleh lebih nipis daripada 0.1 lah. 0.1 is so nipis. It's like 2.5 mm. For vessel, 2.5 is quite low lah kan. Kalau piping dia boleh go lower. And then LMSD. So LMSD is just, to put it very simply, it's tadi someone asked a question about stiffener ring kan. So when we have stiffener ring atau benda yang seangkatan dengannya that is pretty big and macam becomes basically a structure that is welded to the shell, kalau the damage area is too close to that thing and that thing is big enough, FFS diharamkan to do to be performed on that. Bukanlah diharamkan, we have to do FEA lah, finite element, which is a very advanced FFS lah. Tapi paper calculation is not allowed lah if you have that. So LMSD is just a requirement to say that this is the minimum distance you have to be away from any disturbance lah, kata discontinuity they call it. Okay. So the value is 17.9 inch. Okay. Step 6 is a groove-like floor. So groove-like floor ni is something that is not really applicable lah. Groove-like floor ni something where our floor is memang very nipis and very panjang, right? Contoh macam apa? Wolverine, someone macam scratch on the shell or something like that. Kucing scratch on the shell macam panjang je dia punya damage, is like a groove lah, okay? So it's a very limited criteria lah kan. Typically not applicable, but sometimes it can happen. Contoh an example I know is that contoh orang do heat exchanger, they want to pull out the bundle. The tube bundle tu, maybe because of the mechanical pulling, dia kesan dia macam orang cakar the shell. So it could be a groove. Okay. Step 7 is, okay, so this is basically just a back calculation of the PD or PR over SE calculation. If you look at this MAWP, it's basically dia substitute P dengan T. Now dia jadi SET bahagilah R tambah 0.6T. Okay. So it's just same concept as macam T is equal to PR over tu, tapi dia rearrange the term. Okay, instead of P jadi instead of T sebelah kiri, thickness, dia jadikan pressure pula sebelah kiri and dia panggilkan benda tu MAWP. MAWP ni singkatan untuk maximum allowable pressure lah. Maksudnya pressure yang paling tinggi yang vessel tu boleh tahan. Okay. And dia ambil thickness PC. PC tu adalah thickness yang okay lah. So kita nak tahu kawasan yang sihat, dia boleh tahan pressure berapa tinggi. Okay. In this particular case, 367 tu is the highest lah. Yang bahagian yang sihat, bukan bahagian yang tak sihat, bahagian yang sihat. Sebab bahagian yang sihat kena membantu yang tak sihat kan. So, okay. Alright. And then after that, we have our longitudinal parameter 0.17. The thickness ratio tadi 0.3366 kan. And then ada a few other factor yang kita pakai. There is this table called the M punya table, table 5.2 ni, where based on the value of our lambda dengan RT ni kita ambil the M value. Let me show you the table. I hope the screen is okay. I have to go back and it's this table. Sorry, ni yang tadi. Yang ni, okay. Alright, so, okay. I'm not zooming in too much. Let me zoom in sikit. Okay, so table 5.2 is called the Folius factor table. M ni is called the Folius factor. The lambda is, senang cakap, how long, berapa panjang our damage area. And then from kepanjangan of that damage area, and also from that kepanjangan kita boleh tahu apa M factor yang kita boleh ambil lah. Basically, the bigger M factor, the worse lah. Okay? That's the simple way to say here lah. Bigger M factor is worse. M factor is a research number. It's a number that is came up by research. Basically, they do various situation of korot panjang ni, apa jadi. Korot panjang ni, apa jadi. And they just, it's a mathematical factor lah. Okay? There's even a formula to calculate lah kat bawah ni. Tapi, very long formula. Okay, formula. Kesudahan formula ni adalah basically we want to find out the remaining strength factor. Remaining strength factor here is 0.9. This is the final answer. What does this mean? This means that kawasan yang sihat tadi tu, it can take 367 PSI. Kawasan yang tak sihat boleh ambil 367 darab 0.9, which is not too bad. Kan, 90% of the sihat punya capability. That's not too bad. And if you can see here, 0.90404 ni, kalau diorang darabkan, and essentially, dia cakap the longitudinal extent of the floor is acceptable. Maksud dia macam ni, kalaulah value kita tu lebih daripada 90%, halal lah tu. Kira okey lah. Job done. Boleh balik. Okay? So 90% is sihat. So you are okay even if that area is corroded because it can borrow from its neighbor. Okay. Step 9 ni I'll be very quickly. It's just the same thing, cuma the opposite direction. Tadi we will focus on the horizontal area. S kan, you can see S is horizontal, C is vertical kan. Same calculation. Factors pun same tapi nama dia lain sikit lah Tapi ya, ada dia punya own lambda, ada dia punya own RSF, ada joint efficiency sikit. It's nothing too fancy. But at the end of the day, the conclusion that we want to get is our MAWP tadi, 367 tu, adakah dia lebih tinggi daripada design pressure yang kita perlukan? Bahagian sihat tu lebih tinggi ke tak? Tu satu. Second is, kita punya remaining strength factor kat bahagian tak sihat ni, 90.04% ni, adakah lebih tinggi dari 90%? Kalau dua-dua tu okey, lepaslah. Save for operation until, depend lah on berapa FCA yang dia letak tadi. Kalau FCA dia 0.1 inch, tunggulah sampai korot 0.1 inch, dia baru repair. I'm sorry if I breeze through a bit fast on that. I think maybe ada a few questions and I hope I don't lost people. I'm okay to go back and macam re-explain certain things kalau laju sangat. Tapi I hope the basic concept of part 5 is being explained lah. The part 5 basically senang cakap macam ni lah. The longer your floor, lagi susah nak lepas. Okay, that's the bottom line lah of part 5. Okay. If your flaw is just a small dot that is very deep, tapi neighbor dia not too bad, then you should be okay. Alright? And even if your average pun tak berapa okay, that means part 4 tak lepas, tapi part 5 lepas. Okay? I'll pause here for questions.
One question from Umar. Umar asks, apa beza MAWP dan MAOP?
I think MAWP is the official term used in SME code and API, denoting the maximum allowable working pressure. Basically, this is a value that is tied to the full thickness of the vessel minus corrosion allowance. So MAWP ni adalah kalau di luar FFS, dia akan kira based on nominal thickness minus design corrosion allowance. Okay. Tapi for FFS, sebab dia dah corrode, so dia dah tak ada design future allowance, design corrosion, dia ada future corrosion allowance. So dia, konsep dia macam tu lah. Basically, it is the absolute max pressure that you can go safely. Okay. MAOP ni I think lah, to be honest pernah dengar tapi tak berapa ingat the definition, tapi just by virtue of the term is operating pressure kan, it is naturally lower lah daripada working pressure. And I think when we talk about operating pressure, probably there is a function of input from process people perhaps, and also the operator and also the owner of the equipment lah, on what is the safe operating pressure, more from a process standpoint kalau tak silap. Not really from mechanical standpoint. Mechanical mainly MAWP lah yang penting. Any other questions?
Question on the chat currently. Okay.
Alright. So, okay. Kalau tak ada question, okay, I think I can wrap up. I'm a football fan, so sekejap lagi ada banyak match bola ni, so I'm excited about that. So anyway, so let's wrap up. Okay, so in conclusion, what have we learned today? We learned about what FFS is. So FFS by definition is just some calculation procedure to push the equipment beyond its design limit. We learned about what is the typical design considerations for pressure vessel and piping. For vessel, common ones are internal pressure, external pressure, wind dan juga nozzle reinforcement. For piping, the most common ones are internal pressure and weight. We learn about FFS part 4, which the basic concept is about averaging the area between area yang kawasan yang corroded dengan neighbor dia yang lebih tebal. Calculate the area and do the averaging to see whether we can lepas or not. Part 5 is a more detailed calculation which involves the length of the area yang very badly corroded, and based on that length, it links to some experimental constants to be able to tell us what is the remaining strength of that weak area versus the healthy area. And if everything is okay, then dia akan lepas. Part 5 will give you a better answer than part 4, which means people usually would do part 4 first, and if part 4 tak cukup bagus lagi, they will go all the way to part 5. So, okay Zul, we've done part 5. Masih tak lepas ke? What can you do? Repair je lah. I mean, yeah, typically at that point, you really, I guess the options are you have to be a bit more drastic lah, like, more proactive repair, lower the pressure ke, or something of that sort. Okay. Alright, so I guess I didn't, one big thing that I didn't have the time to talk about much kan, is about discontinuity. Some people tanya about stiffening ring tadi kan, I think that's a good point to ask. So remember the FFS, there is some pantang larang that concerns discontinuity. Discontinuity basically if you have stiffener ring or even nozzle or flange, basically any area where there is a significant change in shape and there is a well and significant change in shape. Contoh macam a shell welded to a cone, that's also a discontinuity. So there's a lot of pantang larang for areas that is close to the area. Some FFSs cannot be done on the area if the area is too big or stuff like that. And it's very annoying because those are the areas where corrosion often happens because water trapped at the area, right? So it's a very painful fact to accept, right? But yeah, the reason why we have to be careful with discontinuity is because those are areas where the stress can be higher than what we calculate on paper. That's the short answer lah. Discontinuity tu I don't want to have to explain more lah, nanti panjang pula topik. Please reach out to me if you're interested in that, you know, real case example and all. Overall, I hope this is a good glimpse to FFS. Part 4 and Part 5 is the most common FFS that's going to be used lah widely, because I mean, of course, you want to push equipment, you know, to buy time for repair and all that. Very useful tool lah to be used. So I will send out example, a new calculation ni with all the formulas and all that. And yep,